So hello everyone, welcome to today's quantum space-time seminar. We are very happy to have Sachin Jain from IISER Pune who will tell us about momentum space CFT correlators and its application. Over to you, Sachin.
Thank you very much for giving this opportunity to speak here. I first apologize for not typing, just writing this way due to some issues with my hand, so I could not type. Okay. So, so I'll be talking about momentum space CFT correlator and its applications. So this talk is mainly based on work done with some of my collaborators, Amin, Ranjan. Amin, you know, he was a student here for some time at the IISER. Ranjan is my postdoc. Abhishek, Dhruva, my students. Aditya was 5th year student. And there are some other ongoing work with some students, okay? So the other references that will be very useful, which I'll not refer in the main text, I will also refer to some, will be some work by Maldasana Pimentel on cosmological correlators, Skenderis and his collaborators on momentum space CFT correlator, Sandeep, Nilay, Ashish, Vishal, Subrat, etc. They have done excellent set of work along the similar directions. Then Daniel Bowman and his group members and Enrico Pajer and other people, they also have similar works along the shores. Okay. So this topic, so let me begin with this, that this topic has not got as much attention as its Poisson space counterpart. One of the main reason is that it's quite technically a little more difficult. Even getting a 3-point function in any in CFT 3-point function Poisson space, we know that this is completely fixed. But even in momentum space, that statement is no longer true. One has to really work hard to get those results, and results are generally very complicated, and it's very difficult to sometimes make sense out of it. Second, one can ask what can I learn by just doing simple Fourier transform? Okay. So there are some motivations to understand momentum CFT correlators, and CFT correlators in momentum space finds application in cosmological correlation functions. It has a very nice connection to the S matrix, etc. Feynman diagrams we generally calculate in momentum space. Okay, so one naturally thinks why in momentum space CFT correlators, how their structures are. If I do a Lagrangian based calculation, I will get answers in momentum space. So I really need a structure of moment to understand those. I really need to understand momentum space CFT structures. Other than this, it's not about just taking a Fourier transform of Poisson space. In fact, that is not the approach that we are going to take, and that's not very useful approach. Momentum space CFT correlators has their own light. It's just not as a Fourier transform of Poisson space things. Okay, as will be clear in our talk, in this talk. Even at the level of 3-point function, we'll see there are a lot of new results that comes out. Just thinking from the perspective of momentum space CFT correlators, and interestingly, the close connection to the S matrix, opens up new ways to think about the CFT correlation functions. Okay, so this is a this is a comment about the connection to the S matrix. Point is, there are a lot of results in S matrix that is available, but in momentum space CFT not much explored, and one can think about whether the results in S matrix has a generalized into the CFT correlators or not. We'll see that the results, some of the things that we derive and other people are working, it indicates so. Okay. Other than this, we'll also in this talk we'll talk about Chern-Simons matter theories. And it will be very interesting to look at it from the momentum space perspective. And we'll see how momentum space correlation function enable us to reach interesting conclusions without doing much extra calculations. Okay, just the same calculation that I do to understand cosmology or S matrix connection to the S matrix, the same things readily goes over to the calculations of Chern-Simons matter theory, and then you are able to reach to some very nice conclusions or questions. So, for example, one of the questions that I'll be asking, or it will come out of the calculation in Chern-Simons matter theory, is that does the low energy Hilbert space structure of Chern-Simons matter theory resembles that of the free theory? Generally, one expects that if there is a exactly solvable model, maybe it has its Hilbert space structure is related to a free theory Hilbert space structure. One such expectation was recently realized by Siraj, Amya, Mishra, Tarun, and Navin in their recent paper, where they showed that the Hilbert space structure of Chern-Simons matter theory is like the free theory with extra constraint. They defined Quest-Domino singlet condition, and then they were able to interpret various results in Chern-Simons matter theory starting from the free theory. Here, what I'm talking about is exactly not this, but it's in the opposite limit. Okay, in the opposite, in the following sense, that this is like the high energy higher spin Hilbert space structure that talked about, single particle state, two particles, those kind of thing. But what I have in mind here is like the bound state kind of spectrum. For example, spin one particle, spin one operator, phi or phi operator, or phi or del u phi, that kind of thing, which are like the one can think about roughly as a bound state. These are like the low energy Hilbert space structure. So the results that we will obtain will indicate that even the low energy Hilbert space structure resembles that of the free theory, or will at least we'll see that questions come out of the calculations. Okay. I find it very interesting that to be able to address various questions relating to the S matrix, cosmology, Chern-Simons matter theory, and others, with no extra amount of calculation, that sounds very interesting to me. I'll start with.
Sorry, yes. Sachin, no, thank you for that beautiful introduction. But can I add one more small thing there in terms of, I mean, differences, at least from a more phenomenological viewpoint, when one studies the momentum space correlators from a cosmological context, and at least what I've done, what I normally have learnt about in position space, which is that at least I never paid any attention to contact terms, when I studied my CFT in position space, whereas of course I know you have, whereas in momentum space, in the cosmology context, the contact terms are also important. If you look at the CMB perturbations in the sky, they care about contact terms also. So I think that's another sort of issue when one does momentum space. I feel, especially in the cosmology context, contact terms should be given their due weight, Okay, I just thought I would mention that as a sort of difference.
Okay, yeah. Thank you. And we'll see, actually we'll find out some new contact terms, or, we'll at least point out to some contact terms probably people knew, but I did not see in the literature that explicitly, but it will just come out of the calculations. Yeah. And as Sandeep mentioned, they have their own applications. Okay, so let me first give a brief outline of what I'm going to talk about. So first, I'm going to talk about general structure of 3-point spinning correlators in momentum space, and so how the story is much richer than the position space analog. Okay, we will also discuss connection to the flat spaces matrix, and also discuss cosmological applications. So these will be mainly in the context of 3-point functions. Higher point functions are actually very interesting, but right now I'll just focus on the 3-point function. There we'll see there are already a lot of interesting things to explore. It is well-known result in 3D CFT that any 3-point function of conserved current can be written in terms of free. You have 3 different structures to that. any 3-point function can be written in terms of free fermion, free boson, and parity odd term. And this is a famous work by Prakash, Siroman Prakash, Guillaume, and in. Okay. That there are 3 structures. Any CFT, you can write down any coordinator in terms of 3 structures, and these coefficients are unfixed. Okay. And you would naively think that you require 3 different things, 3 different theories. For example, parity odd thing cannot be obtained from free bosonic theory or free fermion theory. You require parity violating theory. And for example, free fermion and the free boson things are totally different. So you would require at least 3 different theories to get them.
So, sorry, please excuse me. 3 spinning conserved currents means it can be anything, T mu nu, J mu, anything like this. You always have this structure, or is it just for J mu? Sorry.
Any S1, S2, S3. And if the spins are 0, then it becomes 2 structure. If the non-zero spin, depending on the triangle inequality, Si less than is equal to Sj plus Sk. If the triangle inequality is satisfied, then you have 3 structure. If the triangle inequality is violated, you have 2 structures. But if you break the higher spin symmetry a little bit, slightly broken higher spin symmetry, you then again get the 3 structure for arbitrary spin.
Okay, I should know this, but that's okay. Okay, thank you.
However, we'll show that we don't really require 3 structures, just the free bosonic theory. If you take just the free bosonic theory, you will be able to reproduce all these 3 structures, all this free fermionic structure, free bosonic structure, and as well as the parity of structure by doing simple transformations. Okay.
And sorry to keep interrupting, but nothing else is assumed, right? I mean, about unitarity or anything. This is just from the Ward identities.
Yeah, this is just from the Ward identities.
Thank you.
Yeah. Okay, so this is one of the things that we will show that the 3-point function of any conserved currents just can be obtained just from the free theory. I'll be able to write down the full answer just if you tell me, if I just know if I just calculate in the free bosonic theory, okay, including the parity odd one. And we'll see that application of these results to the Chern-Simons matter theory actually reveals something very interesting. We'll find that there's an anionic structure to the correlator. You start with the free bosonic theory. You do some anionic phase. If you add to some anionic phase, it will go to the Chern-Simons matter theory answer. And then it will if you interpolate that anionic phase, it will go all the way to the free fermionic theory. I'll show you in details how exactly it is achieved. We'll also see that this simple way of thinking about gives the 4-point function of spinning correlators in Chern-Simons matter theory. In general, even the following question, that the 4-point function in momentum space has not been understood for spinning correlator. Very recently, just a year back, for scalar 4-point function, how to write down a correlator which is conformally invariant, written in terms of conformal cross ratios, were very recently understood. For spinning correlator, even that question has not been understood. So here I'll be not doing a general analysis, but I'll be applying to a particular theory, which is Chern-Simons matter theory, and there we will see that some very nice result with a little calculation it comes out. Okay. Okay. Yes. Is there any question about it? I'm going to start with the calculation. Some more details.
Sorry. Can I ask one question? You mentioned this triangle inequality for spins. Could you explain where it comes from? Why is there a triangle inequality?
Yeah. So if you give me 2 minutes, I'll actually go there. Okay.
Okay. Great. Thanks.
Okay. Okay, so the way in Poisson space we solve about Poisson space correlators is that we just write down conformal invariant structures and then impose conservation, and from there find out how many independent structures are there. And that is how this conclusion was reached. Okay, that is how this conclusion was reached by first writing down conformally invariant structures and then imposing a conservation. A good Poisson space, momentum space things are a little different. The way you solve is actually you try to write down, you impose spatial conformal transform invariance, what identity of dilatation and spatial conformal transformation invariant. And then you try to, those are all second order differential equation. You have to solve, those second order complicated second order differential equation. And then by solving them, you will be able to find out the answer. Okay, that is the way people proceed. Directly writing down conformal invariant thing is actually very difficult in momentum space. However, for a particular structure, as I'll go, we were able to write down conformal invariant structure even in momentum space, and then using that we could build up the quotas like Poisson space thing. But in general, the strategy is not the same in momentum space. Okay, as will be clear in a minute.
And Sachin, please excuse me, of course you will elaborate, but that result of Shiroman and all you mentioned, it doesn't assume anything about OP structures or anything. It's just a very general result from the general Watt-Takahashi identity conclusion. Huh?
Yes. Yes. So all they assume is that they write down conformal invariant structure and they impose a conservation and they get there.
Okay. Thank you.
Sachin, one question.
Yes.
For 4-point functions, we impose conformal invariance by demanding that the correlation function should be a function only of cross ratios.
Yes.
So
yes.
in momentum space, if I were to impose conformal symmetry in momentum space for 4-point
yes.
function, then is there a similar statement that it should be a function of a particular combination?
Yes, that's so actually what happens is that in momentum space, in Poisson space, the story is that you just write down a function of conformal cross ratio and then you have solved conformal water entity. In momentum space, the story is not that simple. You need to solve second order differential equations, and then if you partial differential equation, if you solve that, very recently the paper by Skenderis and their collaborators, what they were able to show that 4-point function can also be written in terms of some cross ratios, but there are, it's unlike Poisson space, it's all integrated, all expressions are very complicated and they appear in an integration sense, okay? And the conformal cross ratios are also, they don't make sense outside the integration, so it's a little complicated thing. But some such statement exists, which does not have as clear interpretation as the Poisson space analog.
Thank you.
Yeah. Okay, so roughly the Watt identity that you need to solve to get conformal coator looks like that there's a special conformal operator k kappa acting on endpoint function is related to the Watt-Takahashi identity. Okay, what is Watt-Takahashi identity? Watt-Takahashi identity is simply the structure that k mu. Let's say I'm giving you an example. If there's a correlator T mu OO. Then k mu T mu OO is just k mu OO kind of thing. Okay, this is the Watt-Takahashi identity that I'm talking about. What it is actually in Poisson space is the analog of del mu T mu OO delta of x1 minus x2 OO kind of thing, plus permutations. As you can see in Poisson space, you can avoid this by working at a separated points. Okay, if you work on a separated point, this do not contribute. But in momentum space, the point is that because you are doing a Fourier transform, effectively, if you think from that perspective, you have to integrate about whole space time, whole space. So these delta functions will click. So you can no longer avoid this kind of condition. And then this also creates a little bit of difficulty in solving the correlator. But the full thing is that k kappa on the endpoint function is related to the Watt-Takahashi identity. Okay, that is the momentum space spatial conformal invariance. Okay,
I have a question.
Yes, please.
So this on the right hand side of the del mu T mu nu equation, shouldn't you have a del nu instead of the delta function?
I have not been very careful. Yeah, you put del nu appropriate tensor structure. What I was referring to is this delta function. Okay.
Okay.
Thank you. Yeah. Let's take one example and then we'll go over to the spinning thing. If you calculate scalar three-point function of scalar operator, you notice instead of one solution, you get 4 solutions. And the 4 solutions has the following structure. Suppose one of the solutions is f k1, k2, k3. The other solutions are changing k1 to minus k1. This k, when I say k, that is like mod of k vector, okay? 3-dimensional mod of that. These are the 4 structures that you get, okay? However, in Poisson space, you get only one answer. The point is that if you demand consistency with the Poisson space OPE limit, you will be able to show that the B, C, and D, this 3 coefficient has to vanish, and then you uniquely get this answer, and that is the answer that you obtain in Poisson space. Okay, that's like a Fourier transform of the Poisson space answer. So this
one question.
Yes.
So this here is the solution of just conformal invariance, right? What you're
yes.
Yes. Not the conformal Ward-Takahashi identity, because there is no conserved current here. Is this correct?
Yeah. For scalar the Ward-Takahashi identity is 0. Yes.
Yeah. So just imposing conformal symmetry on this.
Yeah. A kappa on O is just 0.
Right. And then you're saying there are 4. So okay, fine. Yes. So maybe you will say, but you will say what these things are in position space.
Yeah. So the story, the point is that there is no analog that you can write down in Poisson space. They are not from the Poisson space perspective. They do not correspond to anything which is constituted in the OPE limit. And I think if you take these answers, if you try to do an inverse Fourier transform, you won't be able to do. There is some singularity that you will hit. So they don't have, in the Poisson space, they don't have an analog. Okay.
Okay.
So Sachin, the consistency with the position space OPE is roughly analogous to having some kind of a regularity condition in momentum space?
Yeah, so let's see. So, suppose you have OO, then it will go as x1 to the power some power times some O, okay? Now, if you look at OO 3-point function, it will be like OO by x1 to something from the OP analysis. So this will translate into, so suppose I have brought, let's say I have brought 2, 3 together, okay? This will translate into K2 and K3 going to infinity with keeping K2 by K3 fixed, okay? And K1, other way of taking is K1 goes to 0 limit, okay? And then you will see that if you just do doing a general 3-point function Fourier transform is difficult, but you can do very simply the Fourier transform of this part, okay? And the singularity structure that you get the singularity structure that you get 1 over k to the power some delta here will only match with this structure. It will not match with the other 3. You have to set BCD to 0 in order to match it, okay? Is it okay?
Sorry, that K there is the sum of the mods or what?
Yeah. So this will be a mod, let's say mod, one of the momenta, let's say mod K1 to the power some power or something, okay?
I see. But I don't see how taking, let's say, K1 to minus K1 will change that. I mean, you would still have that 1 over power, but I guess you don't want a phase. Is that the point?
Sorry, I didn't understand. Say again, please.
No, it's okay. I mean, it's a little technical. I was asking how is it that, because the structures were kind of very simply related, right? By you just analytically continue the magnitudes to minus themselves. And if there is a behavior like 1 over k to the delta, k1 to the delta, then doing that to be the minus, I don't see too much change. But sorry, maybe details are important. Sorry. We can talk later.
Maybe I can show you later. Okay. Yeah.
But sorry, Sachin. Oh, go ahead.
Yeah, go ahead, Sandeep.
No. Okay, Gautam, very quickly, but you must ask. So, Sachin, I just thought I'll say this because it will be nice to continue afterwards the conversation with everyone also, that if I can, which is that, so one of the issues that, I think, but Sachin should say we are faced with then is roughly the following. Sachin can comment, but I think there's roughly a proof that if the operator product expansion is valid, then the Fourier transform from momentum space to position space exists, and the counting works out. There's one answer in position space and one answer in momentum space which satisfies the OPE. So that's the counting, right, Sachin?
Yes.
If I've understood.
Yes.
But you know, the broader question we are faced with, in a sense, is the following. Could it be that the structure of conformal field theories as defined by just a system which satisfies the Ward identities of conformal invariance is more general than what we see in position space, where we impose the OPE and so on? And are more general sets of correlation functions which don't satisfy the OPE but satisfy the Ward identities a consistent, so to say, theory? Okay, so I don't know. I find this very interesting because if it is true, maybe that's what's borne out in nature in the early universe. Okay, I just thought I would say this, Sachin, and then sorry for that.
Thank you, Sandeep. Yeah, this precise. I'll show you where this extra things might actually be important. Okay, so we'll discuss. As Sandeep just pointed out, you know, in their one of their beautiful paper 3-4 years back, they actually found out, you know, these structures were important. Okay, so I'll comment on that.
No. Sorry, Gautam, please go ahead.
Yeah, I think it's a naive question. So in position space, when you were talking about OPE, you were looking at the singular terms, but there are, of course, you know, the infinite series of regular terms in that expansion. And when you are going to the Fourier space, all of those are important. So therefore, presumably the structure of the 3-point function that you see in the momentum space cannot be directly related to the OPE. So maybe this was already implied, but I didn't quite get it.
Yeah, you know, the OP limit that I'm talking about in momentum space, that corresponds to a particular limit of taking some momentas to 0, and I'll be from there picking only the leading order pole from there. And if I take that, if I suppose do that operation in momentum space, I don't have the details, unfortunately, but you know, it's as simple as I said, like, you know, if you take the results and if you do some particular operation, you get some result. Okay, just do, if you do a simple Fourier, you leave out all the subleading terms. But if you do a simple Fourier transform of that, and that is easy to do, then you get some particular result in position space, and that actually turns out to be precisely consistent with if you consider the leading term in position space. Okay, in the leading
singularity in the position space, you can read off from the momentum space by looking at some poles. Is that what you're saying?
Yeah. Looking at some poles, meaning maybe I'll give you a little more details just in the next slides. And
right.
Next, I'll say precisely what exactly it means. Okay.
Okay. Thank you.
Yeah. But one thing that I want to emphasize, apart from here, I will not think about OPE. Here, I just wanted to make a connection with the position space. That's the reason I wanted to bring in this. But apart from there, we'll never think from the position space, OPE, etc. thing. Those kind of thinking is not very useful from the perspective of the momentum space thing. Okay, and even to actually get to here, P, C, D are 0, I don't even need to do this positions consistency with the position space OP limit. Just intrinsically in momentum space, there is a way to understand why the B, C, and D is 0. That's a little technical. And you can just show that BCD can be 0 by doing some momentum space analysis. Okay, so that also exists in momentum space. But for just to make a connection, I thought this would be nice. Okay, let's take an example. If this is taken from Sandeep's paper, if I take 3-point function of dimension 3 scalars, the results are something like this. Okay. This is a little elaborate results, but the point is that everything is, you can show that you can go to a basis where everything just goes over to K1 goes to minus K1. You know, you can translate from one result to other by the precisely the structure I mentioned. Okay, if you do the limit, which I don't have the details unfortunately here, but if you take the limit, as I said, K1 goes to 0 and K2 and K3 roughly of the order same. Okay, this, when I say K2 and K3, these are all mods. Okay. If you take K1 goes to 0, by momentum conservation, roughly K2 of the order K3, then you see that only whenever there's a particular whenever there's only this kind of log of K1 plus K2 plus K3 is what gives rise to the correct Poisson space OP limit. Okay, all the other logs do not give rise to correct Poisson space OP limit. And in fact, sorry, my basis here is a little different. The S1 basis and the M basis that I wrote earlier, only a particular combination of S1, S2, S3, S4, which cancels all the logs of K1 plus K2 minus K3s, all these logs with a negative sign, that is what gives rise to the usual Poisson space result. Okay, so that you can just do by doing a simple analysis, and it is also discussed in Sandeep's paper, for example. Okay.
But shouldn't the position space result be related to the momentum space result by a Fourier transform or something?
Yes, that's what I said. So Poisson space, there is only one result, and that result, if you but in momentum space there are 4 different results. Okay, so one particular linear combination of these 4 different results will give rise to only one solution in Poisson space. So other things do not have a direct relation to the whatever known in Poisson space. Okay, so for example, if you are interested in Poisson space that way of thinking, you can discard all the other 4 solutions you can say those are not connected to Poisson space. Okay.
No, my question is how do you get 4 results in the first place?
Yeah.
How do you get 4?
What you do is that you solve K kappa, this Warthagas identity. These are second order partial differential equation. And these are, as you can see, these are partial differential equations. So you have a much more general class of solutions. And then after solving those, you can actually reduce them to 2 different partial differential equations for scalar. And then if you solve them, you will see that actually it allows for 4 different solutions with 4 different constants. Okay.
Okay.
Okay, good. So till now I have discussed about the scalar case. Let's ask, what about the spinning case? Okay. In general, solving directly in momentum space is difficult. One of the reasons is that there are a lot of degeneracy. By degeneracy, what I mean, there are different structures in momentum space. Those are identical to each other, but if you look at them, it's very difficult to say they are identical. And then when you solve differential equations or when you try to solve, you have to distinguish between different structures, unless you will not be able to get a correct differential equation. Okay? So it's very important to understand degenerate structure, and it becomes very, very difficult in general to do that. However, interestingly, if you work on spinor helicity variables, in spinor helicity variable, it turns out all the degeneracies just vanish. Okay, at least for the 3-point function. And so hence for spinning thing, it's natural to think from the perspective of spinor helicity answer. However, if you keep on solving in momentum space without going to the spinor helicity variable, you will get exactly the same conclusion. Conclusion wise, there is no difference. The number of solutions that you get in momentum space and spinor helicity things are totally identical. But in momentum space, structures are really complicated in general. But spinor helicity answer gives a little better perspective. Okay, so we'll be sticking to the spinor helicity answers, and sometime we'll also refer to the momentum space results. Okay. So the equation again, let me iterate. The equation is like this. So K kappa on the 3-point function is Warthagas identity. One can split this is a second order differential kind of thing. You can split this into a homogeneous part and a non-homogeneous part. Okay, this splitting will be really important for us. So any 3-point function can be split into the non-homogeneous part plus the homogeneous part. The non-homogeneous part is what saturates the Warthagas identity. The homogeneous part, which is K kappa on it, is 0. It turns out the calculation of non-homogeneous part is complicated because you have to saturate the Warthagas identity. You can do case by case basis, but for homogeneous part, we were able to write down conformal invariant structures, and taking them, we were able to just write down JS1, JS2, JS3 3-point functions for arbitrary S1, S2, S3 by just multiplying them. Okay. So the homogeneous part of the thing is much more easier than the non-homogeneous part. Okay. So a little more about the helix structure that will be useful for us. In general, if I have a spin s, there are s number of helicities, plus, minus, and then there are mixed helicities thing. What will be important for us will be traceless symmetric tensors, which are conserved currents. For those, this mixed helicity things are not there. What you get only either plus or minus, and those collectively I denote as plus, or collectively all the minus denoted as minus. Okay, you should think if I'm calling JS plus, meaning all the helicities are plus. Okay, that's the notation. And you can immediately see in the spin helicity variable there are a few independent. How many independent components should be there? When all the spins are minus, all the helicities are minus. 2 of them are minus, 1 is plus, and then there are 4 such things. All minus, or 2 minus 1 plus, and then all plus and 2 plus 1 minus. It turns out for the case of 4, these two are related by complex conjugations. Okay, so yes.
Sorry, Sachin, I'm so ignorant about the spinor helicity formulation. What was the comment just above, that if you take a 3-point function of say J, S1, S2, S3, was it that it vanishes unless? What was this mixed helicity 0? Can you?
No. This is just a particular. Suppose I have a spin S thing. I have various helicities for it, right? It can have mixed helicity, but I'm saying all the mixed helicity things are not there. Only either identical helicity or those are only there. So what are we collectively?
I see. Sorry, just to make sure. Please excuse me. For an arbitrary spin, spin 2, spin 1, higher spin. All the indices have to be either plus or minus. Otherwise, the component is vanishing.
Yes.
Is that right? Okay, got it. And then in 3-point function, of course, you can have the all plus, or all plus, all minus, like that. Those are the various possibilities you're writing down here.
Yes. So there are there are 2 to the power 3 possibilities. Plus minus. So there are 8 possibilities. 4 of them I have written here. 4 of them I have written here. So these are all complex conjugate of each other. Okay.
Got it. Thank you.
These technical details will be a little important for us. That's why I'm going through them. Now,
just one question. You confusing me a little bit. So this J's S1, S2, S3, are they conserved currents or just general operators with spin S1, S2, S3?
Yeah. So I'll be considering in this talk all of them are conserved currents. Okay.
Conserved currents. So there is a conservation equation, right? There is a word identity associated with that also.
Yes.
And that you did not yet talk about, right?
No, those will be very important for what I'm going to talk about next. Okay.
I see. So this could as well have been an analysis of just general operators, right? So far with this word identity that we talked about, this K-mu.
Yeah. I think so. Yeah. In general, if it is not a conserved current, what you will find that the Watt-Takase identity will get contribution. If it is a conserved current, generally Watt-Takase identity has the form x1 delta functions, right? But in general, if it not a conserved current, the Watt-Takase identity will be even 0 from away from contact points. Okay. And they will have their momentum space analog. So in general, classifying what in position space, maybe it is not needed to understand them very well, but in momentum space, I really need to understand what are those class of Watt-Takase identity that are allowed, because that will be very important for us to solve the 3-point function. Okay.
And roughly speaking, you get these pieces if these J's are conserved by partially integrating derivative on J, right?
Say again? Yeah. So del mu Js is 0 if there is no other operator inserted in the usual sense.
No, I mean in this particular left-hand side, you have K-mu acting on JS1, JS2, JS3, right?
Yeah. So this will be actually summation over K, JS1, JS2, JS3, and this sum will actually contract all the 3. Okay.
Okay. Right. So this K is not momentum, right? This K is momentum or
So this k kappa is the spatial conformal transformation generator.
Okay.
Here, this is like the analog of del mu, so that is why this is k mu. Okay, I'm sorry for the notice.
So what is the analog of del mu? The right hand side.
Yeah.
Sorry, I'm a bit confused. The left hand side has a special conformal transformation, and then how come right hand side has a position momentum?
Yeah, a special conformal transformation you write down in the momentum space. Its structure, you will get it has some particular momentum space structure.
I see.
It turns out
one piece. I see. Okay.
Yeah.
So it's the representation of the special conformal transformation in momentum space.
Yes.
They are second order differential operators in the momenta. Abhijit. Yeah.
Okay. So
Sachin, just to follow up on Abhijit's question, so these extra helicities which you dropped out, there are you assuming that these are conserved currents? J's are conserved current when you're assuming that?
If you just assume that it is just traceless, I think they will just drop off.
Thank you.
Yeah. Now, as I said, there are two.
I have a question before you continue. In general, the conformal current is something like x squared del mu or something like that, right?
Sorry, conformal current meaning?
The k mu that you are talking about in position space. In position space, what is the expression for the conformal, this k, the conformal current?
Yeah.
Or the conformal operator? What is the expression in position space?
So the best way to think about is that it's like translation, inversion, translation, inversion. That's the best way people think about.
It has a representation in terms of the coordinates. That's what I'm asking.
Yeah. So I don't remember exactly the form, but what will be important for is that in momentum space you can write down and turns out to be a second order differential equation. Okay.
Okay.
Yeah. Now. As I said, the homogeneous part of the solution in spin helicity variables takes a very simple and interesting, very simple form. And the homogeneous part for spin S1, S2, S3 3-point function, you can just solve it. And by solving, you get actually this solution. Okay. There are two sets of different solutions. One set where E I have defined as mod K1 plus mod K2 plus mod K3. This is one class of solutions for all the helicity. You can set all the helicity, forget about the complex conjugate helicity. You have different helicity. These are the solution. Another solution, which is an independent solution, is this kind of solutions. Okay, these are the two different solutions that you actually get. Now, you can easily get the parity or solutions. Parity or solution is the same solution with a factor of I here. Okay, it's the same solution with a factor of I. Such that when you do a complex conjugation, that factor of I picks up a minus sign, but this does not. But the parity even it does not pick up a minus sign, but the parity or thing picks up a minus sign, and hence, if you convert it to momentum space from the spin helicity variable, you will see that the appearance of a Levi-Civita tensor, and hence that's a parity or term. Okay. Now,
sorry, Sachin, the first structure you've written down, is that the structure you get in flat space? The one which comes as 1 over e to the power something?
That's the structure what I get, sorry, say again, please.
For the flat space 3-point function.
Good. By flat space, you mean the S matrix? Is that what you
mean?
Yeah, exactly. So if I take the flat space limit, you will see that only this part, if you, this part actually gives rise to the flat space amplitude, and this is obvious, right? Then this is precisely the flat space amplitude that you get. Okay.
Exactly. Right. Okay.
And so this is this full thing you just get from the just the homogeneous part. I have not yet spoken about non-homogeneous part, and these are the extra structure you still get in the in the CFT coercions. Okay. So just to summarize, so total I have 8 even and 8 odd, total 16 homogeneous solutions.
Sorry, Sachin, sorry, 1 second. This flat space comment is a little confusing. I mean, will you talk more about it?
Yes, yes. I'll talk a little more about it. Okay? Yeah. So now we see that there are in total 16 homogeneous solutions. I have not yet counted how many non-homogeneous solutions are there in momentum space for spinning correlator. And if I demand consistency, 8 of which is parity even, 8 of which is parity odd. If I demand consistency with the OPE, Poisson space OPE, you will see that actually only one even and only one odd survive. All the other things just drop out. For example, you'll be able to show if you just demand consistency with the OPE, here only this solution survives, not any of these solutions survive. And from here also, only when all the helicities are minus or all the helicities are plus, that only survives. Okay. So you have one even and one odd solution that survives.
Sachin, sorry, just to make sure I understand that. So if you demand OPE, then say if you take the stress tensor 3-point correlator, you have one even, one odd. And if I then allow parity violation, I get one more of each kind. Is that true? That sounds too much somehow.
Yeah. So what I'm referring to here, Sandeep, is just the homogeneous part. And homogeneous part, if you go for TTT, you will get one even and one odd homogeneous. Now I'll come to non-homogeneous. There will be some more structures will be there. Okay.
Oh, okay. I'm sorry. Mm-hmm.
So sorry, Sachin, this consistency with position space OP is a bit confusing. I mean, so how is it that, how exactly this is happening? I mean, so you said that the Fourier transform of these other structures just does not make sense. There should be some way to write them in position space. I mean, I'll bet with the structures that do not have any good OP interpretation. But nevertheless, is there a way to do this in position space?
Yeah, one quick way of seeing it, Abhijit, is that if you look at these structures, for example, if you set, let's say, K1 goes to 0, you will see that there are extra K3 goes to K2, there is extra singularity, which is bad from the Poisson space OP limit, and hence they are not there. And also here, if you look at away from, if you look at, say, minus, unless you look at minus helicity for this thing, all the H's are minus. If you look at minus plus helicity, you will see that again, the bad poles start appearing here, okay? And then those are also not good for from the perspective of the Poisson space OP limit.
No, let me ignore the position space OP limit.
Yeah.
Can I just write down the position space form?
Yeah.
You are saying that form would necessarily be somehow. I don't understand. I mean, let me not impose any condition on what my position space function is. I just want it to be conformally invariant.
Yeah.
Can I just write this down in position space?
I don't think so. If you just demand conformal invariance and if you just demand conservations, you just uniquely get to one particular result. You don't get anything else.
But just to follow up on that, so presumably it means, as you people were saying, that you can't Fourier transform this function.
Let me say that this is what Shiraz told me. After I was confused for like days, he said, this is what must be happening. Then we checked in the literature. Go ahead, Shiraz.
No, but I want to understand, what is the obstruction to the Fourier transform? Is it like these funny poles? K3 plus K2 minus K1, that kind of thing is the obstruction to being able to Fourier transform?
Yeah, I think so, yes.
So suppose we regulate that for a moment, just to understand. You put a cutoff there, then you can Fourier transform.
You mean the cutoff in the pole structure? Let's say I don't allow for K3 K2 pole to happen.
Yeah, you allow K1 K2 K3 to go not too near the pole, then just block it off. Somehow regulate that singularity.
You're saying that if I try to do a Fourier transform, this will be maybe a one-dimensional space of points. If I ignore that one-dimensional space of points, I can
regulate. Put a regulator. So change this function so that instead of going to infinity at that pole, it goes to some large value and stops. Just to get a sense for what's going on.
That's some I epsilon description.
Maybe an I epsilon. I was thinking
pull off of the axis and then it will give you the bump rather than.
Yeah.
I think of it that way.
For instance, yes.
Okay.
Just to get a sense for what's going on. We can talk about this later.
We have not really tried to do that Fourier transform as of yet. Trying to, as you pointed out, Siras, maybe it would be interesting to just put I epsilon or some cutoff and do a Fourier transform and see what kind of structure it is. That we did not try yet. But it will be of something very different kind of thing, which will not look like any so the structure should at the end also have conformal invariance and also conservation properties in position space. That if I try to do independent analysis, that gives me only one answer. So it's very difficult to imagine to get another thing, but maybe there is something.
Okay, thanks.
Just to say, sorry, Sachin, please excuse me. I think it's a very good point, because I have also not, that paper of Skenderis, I have also not studied it, right? Exactly what is the obstruction to being able to compute the Fourier transform, right? And is it could just be that the most general solution blows up too rapidly in some region at large K, right? It need not be when they come together. Or they come together in some co-dimensionality. Anyway, okay, it will be nice to do. You're right, Shiraz. Yeah. Okay, sorry.
Yeah, sorry, I have not really thought about that question. That how to do a Fourier transform of this. That maybe we can do and then talk about it. Okay. So if I demand the consistency with the OP, as I mentioned, there is only one parity even and one parity odd homogeneous thing that survives. If I have the triangle inequality when it is satisfied, for example, if you take TTT 3-point function, you will be able to show that the Watt-Takase identity, now I'm talking about the so till now I have spoken about the homogeneous solutions, okay? And let me in the range when the triangle inequality is satisfied, for example, if I take TTT, Watt-Takase identity, the Watt-Takase identity for TTT that appears on the right-hand side, it's a TT 2-point function that can be parity even and parity odd. And doing a simple analysis, you can show that the TTT non-homogeneous have a non-homogeneous even part, and TTT odd part has a TTT non-homogeneous odd part to it. Okay. So there are, in general, there are actually 4 structures: two parity even, 2 parity odd. So I get 2 even structure, 1 homogeneous, 1 non-homogeneous, 2 odd, 1 homogeneous, 1 non-homogeneous, and the homogeneous structures correspond to W cube, non-homogeneous structure correspond to root G R, another homogeneous parity or structure correspond to W tilde W square, and the non-homogeneous structure, which is a contact term, that is related to W tilde. So this is a general story, and this can be actually generalized to any arbitrary spin as long as you are inside the triangle. Okay. So
sorry, just to understand. So you say every time we have a non-trivial 2-point function, we have a new non-homogeneous solution.
Exactly.
Right? Yeah. And you say there are 2 non-trivial 2-point functions, 1 parity even, 1 parity odd. Is that right?
Yes.
And the parity odd 2-point function was a contact term?
Yes. A parity odd 2-point function is a contact term, and then you can show the parity even thing also. The 3-point function will also be contact term.
I see. The parity odd 2-point function was a contact term, and that was basically I see. Okay, thank you. Yeah. Just for the parity odd 2-point function, that is the 2-point function that comes from taking this W tilde and taking the quadratic part of in H.
Right.
Yeah. Okay. Thank you.
So it's very interesting story that this root GR that gives rise to TT even, and the same root GR will give you TTT. That is a connection for the non-homogeneous. It gives rise to 2-point function as well as it gives rise to 3-point function. That's the thing. So this is, I'll be referring them to as non-minimal, and this I'll be referring to as a minimal. Okay, because number of derivatives are different. So to match this with the known story, there is a 1 free fermion, 1 free boson, and 1 parity odd. That was Sirman and other people who were results. But you see, because they were working in position space, they missed this contact term, but which in general is there for arbitrary strings. Okay. Moreover, there is a very interesting thing that immediately actually follows from this analysis. As I said, parity even and parity odd in spin helicity variables are related by just a factor pi, which if you convert that into momentum space, gives rise to this relation between parity even and parity odd. Parity odd homogeneous term is just some epsilon transformation of parity even homogeneous term. Okay. This I call as a epsilon transformation. So I take the parity even correlator, I do some multiplication with the epsilon, contract with some indices, and depending on, these are the momenta. When I my notation epsilon epsilon k1, k2, k3, suppose I have, so that's like epsilon mu rho, k1 mu, k1 mu, k1 sorry, k2, k3. Yeah, that is my notation. Okay. So you see, the even and odd thing, they become just some simple epsilon transform of the thing. And if you try to go to the Poisson space, this will become an integral transformation. Interestingly, these were not the things that were understood in Poisson space, that there is a relation between parity odd and parity even. But in momentum space or spin helicity variable, they just become apparent that they have to be the case. Okay. Now you can do a little.
Sorry to be so slow. So that relation you've written down, Sachin, that is now in general, right? Not in some spinor helicity basis, if I understand. I just take the 3-point function, the odd part of it as in terms of 3 currents, and I can obtain it from the even one by contracting some of the indices with the epsilon tensor involving the momentum also. That's the relation, right?
Yeah.
I see. Okay. Thank you.
Interestingly, if you do a little more careful analysis,
I have a question.
Yeah.
In general, when you have such 3-point functions, they lead to a star in the sense of, I mean, you have 3 propagators attached to each other, forming a delta. Sorry, not a star, but a delta. And in general, if you follow Rajesh's work, earlier work on this ADS CFT thing, these stars can be converted to these deltas can be converted to stars. So you have these propagators joining each other. They can be converted to something where you have propagators emanating from the sources and meeting in the middle. So they form a star. And that in general, I think, can be Fourier transformed and given a momentum space representation. I'm just suggesting that you look up Rajesh's work and see whether it has any connections.
Okay. I'll look into it. So here the comment I was making is that you can do very easily Fourier transform this, and then what you get is actually in Poisson space you get a very complicated kind of relation in Poisson space also. Okay. So if you look at it more carefully, you would be able to show that the free fermion result in 3 dimensions and free boson result in 3 dimensions can be split up into non-homogeneous plus homogeneous, and free boson can be split up into non-homogeneous minus homogeneous. Okay, it's the same non-homogeneous thing that appears in free boson and the free fermion when you have triangle inequality is satisfied. Okay, inside the triangle, the Watt-Takase identity for free fermion and the free boson are the same. And the question that Abhijit, you were asking, what about the conservation? For higher spin thing, you can just write down using higher spin equations this Watt-Takase identity. If you are inside the triangle, they are the same. Okay, and hence the non-homogeneous results have to be the same. And if you do a little more calculation, you understand that the free fermion and the free boson results are actually, they are just simply can be written like this. Okay, the same homogeneous thing that appears, same non-homogeneous thing that appears. And the parity odd result is just if you take this homogeneous part, which is free fermion minus free boson by 2, and then do epsilon transformation, that generates the parity odd thing. Okay, so this is the comment I wanted to make, is that the free bosonic result, if I know free bosonic result, that generates all possible 3 structure. I don't need to talk about 3 different structure. Given free bosonic result, it is easy to distinguish between what is homogeneous and what is non-homogeneous. Once I have distinguished, I have taken the homogeneous term, done an epsilon transformation, I got the odd. So I get all the 3 structure just from the free bosonic theory. Okay.
Sorry, but I thought you have an odd, which is a non-homogeneous also.
Yeah, non-homogeneous thing is a contact term. So in Poisson space, they are all neglected. So I'll not be yeah. So that's a separate yeah. But you know, just in 2 minutes, I'll come to one different kind of parity or thing that will be very useful when I try to make a connection with the flat spaces matrix.
Nice.
So story actually becomes
sorry,
that you were asking about. Sorry,
the odd contact term would be non-universal, right? I mean, you could add, you could change your theory by adding a little extra piece.
Yeah.
Okay.
Sorry, I didn't understand this comment.
What I meant was that suppose you compute you have your partition function of your, let's say, suppose you have, let's say, the stress tensor. You compute the all correlation functions of your stress tensor. And that's some function of metric whose Taylor coefficients are the correlation functions of the stress tensor. Yeah. Now to that, if you just add this extra contact term, this W tilde, that would change your 2-point functions and 3-point functions by this contact term way. And it could just be that you're changing your microscopic definition of the theory a little bit by adding this extra, local contact term, your partition function, for instance, or something like that. So some of these contact terms are just not universal, right? That you can tune them as you want.
Okay.
Yeah. Like you're saying, they roughly correspond to adding a local term in the
action. Yeah, right.
In the action.
Local non-dynamical term in some sense. So you have the freedom to do it.
I see. Non-dynamical. Huh?
Because here's just a function of the metric.
I see. Okay.
For derivatives, you mean?
No, derivatives of metric, but not of the dynamical fields of your theory. Okay. Let's say we're doing quantum field theory and the metric is just a background field. Okay. When you couple the thing to metric, you could also add extra local terms with the metric. When we say we take the theory and we turn on a background metric for the theory, integrate out all the fields. In that process, we could have just added some local contact terms just purely for the metric for fun, right?
But these other odd terms, for example, they don't have that interpretation.
No, anything that's non-contact can't be this way.
Yeah. Right. Okay.
Yeah, like it reminds me somehow of this game they play in these Chern-Simons theories, right, Shiraz? I mean, they define the current, okay.
Exactly. Now in Chern-Simons theories, however, you can only add things up to integers. Right? Because the Chern-Simons coupling is only well-defined up to integers. So if you get somehow you manage to generate a non-integer part, then that part is physical. That can't be changed by adding a local counter. Right? But here I don't see any analog of that unless I'm missing something.
So this could be formulated in terms of the descent equations, etc.
Yeah, presumably. Yeah.
But okay, no, Sachin must go on, but just to flag things for further discussion. I mean, are you saying that perhaps it's just a definition dependent thing, Shiraz, or what?
Yeah, I mean, often that's the case with contact terms, right? That at least if you're just doing quantum field theory, sometimes contact terms are physical and sometimes they're ambiguous. Meaning you could change the theory a little bit to change what it becomes. And somehow it's very important to know which terms are universal and which terms are.
Yeah. The reason I want to, sorry, Sachin, but I want to discuss this with you all later offline is, I mean, in cosmology, it really makes a difference. Seemingly some contact terms really change the, non-Gaussianity. And okay, it would be nice to understand this a little bit better, if you don't mind, how to decide that.
I would love to answer. This is something at least I personally have never completely understood.
Yeah. Because, in the contact term, suppose I'm doing Chern-Simons theory, if I have a non-integer part, I think that I cannot remove, right? That will be important, right?
Exactly.
The integer parts I can remove.
Exactly.
Yeah. But here, like for TT and all that, there's no analog of that, right? As far as I know. I don't know. Okay. I'll bug you.
If you Chern-Simons theory, if you actually do a momentum space calculation, you actually encounter this TT 2-point function, which is not integer, but lambda. It is lambda dependent. The Chern-Simons coupling lambda dependent, and you can only remove the the integer part It was a very important thing for us when we were trying to understand the structure for momentum space in Chern-Simons. Exactly the same story for 3-point function also. If you do a direct calculation, you will see actually there are contact terms, but those contact terms only you can remove the integer part by adding, as Siraj said, by background field you can add always a integer terms which can remove the integer part, but in Chern-Simons you get those extra non-integer parts also.
I see. Okay. And I won't slow you down, but I guess the question then I would have is, suppose you only had the bulk, you didn't know your theory was Chern-Simons, you could still come to this conclusion that there is something you cannot add by way of a WW tilde kind of bulk interaction, which presumably is the real content of your contact term. So something like that, huh? Okay, I'll ask you all later. Okay, thank you.
Okay, so this is just to address Siddharth's question, is that what happens, where is the actually triangle inequality comes into the play. If you go actually outside the triangle, the story becomes totally different than inside the triangle. It turns out for outside the triangle, there is no homogeneous solution that is allowed, which is consistent with the position space OP limit. It's a simple one-line calculation, okay? And then immediately you reach that, that there is only only non-homogeneous solutions are allowed. However, it is known by the previous work that there are two, for exactly conserved current, there are actually two even but no odd. How it gets out from our calculation is that the parity odd non-trivial terms are always homogeneous. So outside the triangle, they cannot exist. Okay, that is a simple proof of why there is no parity odd things. But how about only two even? Because as I saw, the non-homogeneous things are unique. So how can I get two answers? That was a little bit of puzzle for some time for us, until actually we looked at it more carefully about the higher spin algebra. And what we figured out very interestingly, that inside the triangle, Watt-Takase identity for boson and the fermion are the same, but outside the triangle, Watt-Takase identity for boson and the fermion are not actually the same. And they will lead to two different non-homogeneous even answers. And that also immediately tells you that you will get two different non-homogeneous parity odd contact terms for the 3-point function outside the triangle, okay? Using the same thing. Now, if I go for slightly broken higher spin theory, then it is known that you can still get parity odd answer. The way you get it from our answer is just take again the free boson and the free fermion answer that we calculated just here using their this thing, and you just do epsilon transformation again, and it turns out the Watt-Takase identity is just given by the difference of Watt-Takase identity of free boson and the free fermion with the epsilon transformation. And interestingly, this Watt-Takase identity you can derive it using what are called non-conservation of higher spin, slightly broken higher spin. If you take conserved current Watt-Takase identity, do it fermion minus boson, you do epsilon transformation, you precisely generate exactly the non-conservation of higher spin equations by doing this procedure. Okay, so somehow slightly broken higher spin symmetry, somehow the exactly conserved currents knows about the slightly broken higher spin symmetry theory. Okay,
this is an observation, I guess, huh? But I mean, why does it work like that? I mean, is it just the structure of those right-hand side terms is such, I guess, huh?
Yeah, so we actually explicitly checked for a few examples, and this works. And then actually we went ahead with higher spin equations, and in general we could prove this statement.
I see.
Like we took a general higher spin equation and we could actually prove this statement.
And just make the statement one more time, please, Sachin.
Yeah. The statement is the following. We have checked for 3-point function series, but I think this would work for any higher point function. But for 3-point function, statement is the following. Suppose I have a higher spin current, spin greater than is equal to 2, greater than 2. If it is not conserved, it is weakly broken. Roughly the structure is with some many derivatives here, which I am not writing. Appropriate derivatives is roughly like this. JSI, JSJ, these are the double trace kind of operators. Now, if you calculate for example, this kind of 3-point function, let's say for simplicity, let's make it J1, okay, for the moment, because they are conserved. Then if you take del mu here, you will find, you use this thing and you find out what is the Watt-Takase identity that is satisfied, okay?
Yes.
You get something like this. Then you do the following. You take free bosonic answer, free fermionic answer, Watt-Takase identity, free fermion and the free bosonic Watt-Takase identity. You subtract them. You do the epsilon transformation that I talked about in the previous slide. That precisely matches with this once you calculate this. Okay.
Wait. Didn't you say that the Watt identities were the same for the two if S1, S2, S3 obey a triangle inequality? So maybe I'm confused, sorry.
Yeah, no, inside the triangle, actually, you automatically get the parity odd thing, and then you can show that this non-conservation thing never clicks. Here, you can show that it never clicks. Okay, the parity odd thing just comes from the homogeneous thing. Only when you are outside the triangle, this non-homogeneous thing starts clicking. Okay.
I see.
Yeah, that's a very important. It's a detail, but very important point. Yes.
I see. So you say you take free boson minus free fermion, do this epsilon transformation so as to get something, a parity odd guy,
yeah.
And that is the same as what comes out of this JJ on the right hand side.
Yes.
Wow, amazing.
I have a question.
Yeah.
Apart from the 4J term, aren't there other terms which just have JS1, JS2 and the delta function or something?
Here, even here. So these are at the same location, okay? These are at the same location, so it factorizes here, okay? And here, this just comes from, due to this, there are also triple trace things, but those are all subleading, so we are not considering them, okay? And this is what exactly is this? There is no extra term or anything.
No, but on the right, I think what he's saying is even for a conserved current, there would have been the transformations of the other two J's, right? Like if you take d mu of J S mu with say JS1, JS2, then you would have had the transformation of JS1 and JS2, right? With delta function contact terms.
Yes.
And here, those extra terms you're not writing, right? Because maybe you're in position.
Those extra terms, just give me a minute to think. We actually thought about this thing. I have to just.
I mean, if it doesn't throw your talk off, yeah.
Maybe I can just comment on it. Just have to think for a minute. I can just. Yeah. Okay.
Wait, just to get, I thought that you were saying that it's those extra terms, the difference between that of the boson and the fermion that reproduce this JJ.
Yeah, exactly. So right? What happens here? Yeah, exactly. So here you see there is a delta function, right? But if you do epsilon transformation in Poisson space, you see that the delta function goes away, and then the effective, effectively it becomes a non-conserved. Okay.
Oh, I see. So, okay. I'm sorry. I misunderstood then. It's those terms which give rise to this.
Yeah. So, sorry. The point is, Sandeep, what you are asking about, those things will not contribute here. But what can contribute is due to action of this here. Okay, action of this here. If you are taking to be conserved here, but they will never click. You can show they will never click. Okay.
Wait,
a little bit of detailed calculation.
Sorry, and so now suppose we took a product of 5 J's, let's say.
5 J's meaning where it does here.
To start with, you take d mu on some product of not 3 J's but 5 J's.
Yes.
Okay. Now the Watt identity will give you stuff that has products of 4 J's on the right hand side.
That is right.
But the non-conservation equation, the Maldacena-Zhibodev non-conservation equations always have either 2 or 3 J's, right?
Let's see. Let me just try to work out. So if you have JS, let's say you have J. Let's say this is a scenario that you are talking about, right?
Right.
So
exactly.
I thought about up to 4, but 3 here. What happens? You are totally right. I'll get J, and then this in general can give rise to this kind of thing, and you will get the 4-point function also, as well as also 3-point functions both. So this can factorize into JJJ and JJJ plus JJ 2-point function plus 4 times 4-point function. Right? There are two different factorization that is possible here, right?
I see. Thank you.
And the exponential transformation, I think, will just reproduce the four thing. I have not thought about those 3 things. That maybe come also from something.
I see. So you say that just to summarize, from the word identity, if you act on an n-point function,
yes,
the usual word identity would give you an n-point function, n-1 point set of j's. Now you say using the Maldacena-Zhibodev kind of equations would give you, if you just use the JJ, you would apparently get an n+1 point function, because you get 2 j's and then n-1. But then you weak contract one of the j's from the 2 j's and one of the j's from the other guy, and that leaves you with n-1. And that's how it works. And then the 3 j's will play some other role.
3 j's, I think, maybe if I just try to be more careful with the counting, maybe they will contribute. But I think what will happen, Siraj, is that they will not be as they will be like a contact term as compared to this 4j things for a 5-point function, right?
Right.
Yeah. So they will be. You might be able to just do a contact term redefinition kind of thing, and then maybe you can interpret that will not be definitely at the same structure as a 4-point function. If it's the 4-point function that appears on the right hand side.
Amazing. That's totally amazing. Yeah, thank you.
But just one question: why are we contracting the J from this group to the other group?
Yeah, we were at the same
large
location.
and counting.
Yeah, large and counting. These are all slightly weakly broken height spins. Yes.
Yeah. All of these equations come with a 1 over n.
Yeah.
So you need one contraction to get rid of that.
That's cool. Thanks.
Okay.
Just to ask you one last thing, there's a similar, one of these is also applicable for the stress tensor is of course exactly conserved, right?
Yes.
So it starts with spin 3 onward, right?
Yes, spin 3 onward. That's right.
Okay. Thank you.
Yeah, and for the conventional things, these things may not be very, very important, but from higher spin thing, which I want, so there it is.
Sure.
Okay, so let's answer the following question then. In general, there are 16 homogeneous solutions. We only could account for 3. Is there something? Are they good for anything else? Okay. This is what Sandeep was previously also mentioning. I'll just give a very quickly a little bit of details. Okay. So how much time do I have? I'm sorry, it's already, I said 12:21.
How much longer do you need, Sachin? We can of course go on longer than as long as you want.
Okay, so I'll be, the other things are not, it will not take much time. So maybe 10-15 minutes, I might be able to.
Yeah, 10-15 minutes, no problem. Yeah, but please don't feel pressured to complete on time.
No, let me point out that Sachin is on slide number 16 out of 40. So.
No. Things will be, I showed a little more details, but the conceptual things I can say, and then maybe we can discuss it. So. Just give me 1 minute. I need to put on charger. Sorry. Okay. So to answer this question, that there are 16 homogeneous solutions. Is there anything good about them? So to answer that question, just look at, now I'm going to look at the S matrix, 4-dimensional S matrix of three gauge fields, okay, massless gauge fields. That is what I'm going to look at. And then you can just classify them, gauge invariance and other things. You can just classify them in terms of, for most general S1, S2, S3, you can show that there are actually 4 structures, okay? two parity even structure and two parity odd structures. And the two parity events will be like, they are again minimal and non-minimal. Minimal in the sense less number of derivative, non-minimal is more number of derivative. Okay, that is the general structure. You cannot have more than 4 covariant answers. Okay, that is the first thing that you see. Here the notations are epsilon, Z1, Z2, Z3, P1, meaning these are contracted like this. Okay, that's the notation. This will not be very important what I'm going to discuss, just in case you are interested. The notations, etc. Now there's immediately one puzzle. If there is a connection to the flat space, connection to the CFT correlators with a flat space amplitude, so the connection is that 3D CFT in some limit goes to 4D scattering amplitude. Okay, that's the connection. If there is a connection, but 3D CFT, you have seen that there are actually 3 structures, right? But here I see 4 structures. Then how can I generate one more structure? Just to mention, the contact term is not going to help you out with that extra thing. But what is going to help you out is I'm going to tell now. Okay. Roughly, if you take the 3-point function, if you define the following quantity E, which is mod K1 plus mod K2 plus mod K3, and if you take E goes to 0 limit, roughly this thing we have checked it, shown it explicitly, because we have a general expression for the homogeneous term. If you take the homogeneous parity even and parity odd, take this limit E goes to 0 limit, the singularity goes as E to the power S1 plus S2 plus S3. That's the leading singularity term, and the residue of it give rise to non-minimal odd and even term. Okay, so non-minimal odd and even, non-minimal odd and even are reproduced by the homogeneous even and odd term in the CFT. Okay. Now, if you take the non-homogeneous,
sorry, Sachin, I won't slow you down, but among the set of things to learn from you and everyone else, why is this the correct flat space limit? I'm embarrassed. I don't understand. I mean, in the context of ADS, I should be able to understand it by building some small elevator inside and all that. But I mean, okay, later you all of you explain.
I can just give a 1-minute thing from the CFT perspective. Why?
Thank you.
Then, from ADS perspective, Siraz and Abhijit, they have explained to me. But roughly what happens is that, you see, in 3D CFT, you have momentum conservation delta 3 of P1 plus P2 plus P3, right? But in 4D, flat space amplitude also has extra momentum conservation, which is energy, right?
Yes.
Which is mod P1, mod P2, mod P3.
Correct.
So by taking this E goes to 0 limit, I'm actually doing that. I'm just imposing extra that thing.
I see. So it's a little bit like one of the things you continue to negative energy in a sense, and that's why you're doing.
Negative energy, or take momenters to complex this thing, and then that will be important for us to think from that perspective.
Okay, go ahead.
And somehow this limit should also be related. Is also related, I think, from the ADS perspective. It should also be related to taking L to very, very large, such that it becomes factor. So Siraz, Abhijit, they know better.
Okay. Thank you.
The non-homogeneous event term actually goes to this minimal event term. Okay, and these are the 3 structures that was the Poisson space analog of the 3 structures. Now, where is the 4th structure? Without much this thing. The 4th structure is simply you take the non-homogeneous event term, do the same epsilon transformation that I introduced, and then you take the flat space limit. It correctly reproduces the correct odd minimal thing, okay, in the flat space limit. And you can show it very easily. Here you see, if you find out the Watt-Takase identity for this kind of correlator, Watt-Takase identity is Watt-Takase identity of free fermion plus Watt-Takase identity for free boson, and then do a epsilon transformation. This turns out to be the case that here no longer this structure, just doing this epsilon transformation, you can show that this no longer corresponds to any conserved 3-point function. Okay, this corresponds to non-conserved currents. Okay, this extra structure. So in order to reproduce this extra this thing here, minimal parity or thing, you have to consider at least one of the currents to be non-conserved. Okay. That is the story. Let me just give you one quick example.
And does that mean that the corresponding bulk field is massive?
Yeah, I think so. That it should be that the bulk field I think should be in a very particular way. I don't know exactly how, such that in the L goes to infinity limit somehow it has to mass should go to 0. Now that should be the case. I actually don't understand what is happening. It sounds in ADS also there should be analog of this thing, but I don't really as of yet understood that point. What exactly is the term?
Okay, thanks.
But I have a comment about it. Sorry. Yeah. Sorry. Go ahead. Sorry.
Yeah. So in terms of when you're considering say ADS CFT correspondence in terms of Witten diagrams, when you have 3 operators on the boundary, in the bulk perspective, they correspond to a tree that is joined to all the 3 operators in the middle by at some point. That's right.
Yes.
So in general, can't you take a simple Fourier transform of that kind of a propagator and get the Fourier transform directly instead of trying to get it from the Ward identities and going through all this process?
Yeah, these are very good questions. The point is that doing Ward-Takase identity by now has become very straightforward. By straightforward, I mean it has been systematized. The point is that you learn much more from here, and then you try to. We are doing abstract CFT analysis without referring to any particular Lagrangian or anything. Then I can go ahead and try to match what you are saying. But we'll see that this kind of thinking is very important. That gives rise to a lot more extra structures that other than what you can think about the way you are thinking. Okay.
No, but my point is the extra structure seems to be an artifact of the Ward-Takase identity. Is that correct?
No, as I'm going to explain in a minute, that those has some physical meaning to it. Okay.
Okay.
Yeah.
Sorry, Sachin, maybe this is related, but there were some of these structures that you had discarded, saying that they are not quite consistent with the position space OP limit because they had K1 plus K2 minus K3. So can one talk about their flat space limit also?
Yeah, good. Just if you give me a minute, I'm exactly coming to that. Okay. Okay. So just to elaborate what happened here about the epsilon transformation, let's take a simple example of TOO, and then you get a parity even answer. This is a non-homogeneous. TOO is there is only non-homogeneous, and TOO there is only one structure that you can write down. Okay. Now let us do a epsilon transformation of it. Epsilon transformation of it actually gives you this answer. Okay. And if you take the flat space limit, you exactly get this structure. Okay. Interestingly, yeah, you exactly actually get this structure. Yeah, so, sorry, I said in a little different order. I'm sorry, I have to say just one minute. Sorry, I mixed up. Yeah, let me first try to answer what Abhijit just asked me. Okay, so Abhijit is asking that which part of the CFT correlators goes over to the flat space amplitudes. Okay, so let's first write down what is a flat space amplitude. The flat space amplitude actually is just given by this. Okay, in 4 dimensions, by just doing some simple analysis, you can come to that in the spin energy variable, it is 1 to the power h12, 1 3 to the power h13, 2 3 to the power h23, and h1 to h13 and h23s are given by this. Okay, these are h's are some helicity and s's are spin. So this is for spin s1, spin s2, and spin s3. And then because of the helicity, there are only 4 helicities that I discussed: minus, 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 or 2 minus 1 plus. Other things you don't take. Then the parity even and parity odd, there are 8 even, 4 even and 4 odd. So they correspond to there are total 8 amplitude, 4 even and 4 odd. They correspond to those 1 over e to the power some results that I actually showed earlier. I'm sorry, I have to just go back to that thing once. Yeah, these correspond to exactly these structures. Okay, and there is no, they don't correspond to these structures. So in the e goes to 0 limit, there is no consistent way to define a flat space limit for these structures. Okay, and the structures that I talked about, they precisely match with these structures. Okay. That here also you see there are 8. In spinelessity there is also 8. Okay. Now this immediately leads to a very interesting puzzle. The puzzle is in the covariant sense. I have shown that there are only 4 covariant amplitudes, right? 2 even, 2 odd. In spinelessity variables, I'm showing there are 8 amplitudes, 4 even, 4 odd. So what's the counting going on? Earlier I said 4 covariant. Now I'm saying 8 spinelessity. There's already a mismatch, right? You know, in covariant there are 4 only maximum you can write down. You cannot really do anything more. In spinelessity there are 8. So already at the flat space limit there is a mismatch. How do I? So here is a little table which actually discusses this mismatch a little more.
Sachin, sorry, just in case I'm losing the thread, are you saying if you write down the S matrix in flat space,
Yes.
in a covariant fashion, you get, say, 4 independent terms which can appear. If you write the S matrix in spinor helicity, you get 8. Did I understand right?
Yes, exactly.
Okay. Thank you. Go ahead, please.
Let me amplify one particular case which will explain the difference. So one particular case is when my 2 of the spins is 0, one of the spin is spin S, like TOO, analog of graviton 2 scalar. In 4 dimension covariant thing, you can just write down only one parity event. You cannot write down parity odd. The simply reason is if you have epsilon mu rho sigma in for 4 dimension, the J, the polarization tensor, let me call them polarization tensor, P1, P2 nu sigma, you cannot really contract one of it. So mu sigma I have contracted, rho is uncontracted. There is no variable to contract, right? So you really cannot write down a covariant answer for spin S 0, 0. It's not, the data is not available. But in spinor helicity, that's very simple. In spinor helicity, what you do is that you just write down the same amplitude and the parity odd is just a factor of pi. That's all. Now, let's try to understand what is happening from the CFT perspective. Actually, it's very interesting.
Just quick question here, Sach. You know, this bulk 4 dimensions, right?
Yes, bulk is 4 dimensions, yes.
Now, in 4 dimensions, the massless little group is SO2.
Yes.
And the spin 1 and spin -1 representations of SO2 are just completely different representations.
Yeah.
Yet CPT tells us that they always come together.
Yeah.
So I was wondering whether you're getting somehow doubling by ignoring that last thing.
CPT.
Yeah, by ignoring CPT. That is by pretending that what spin 1 does has nothing to do with what spin -1 does. It's probably wrong, but I was just...
Yeah. So, you know, for the momentum, for spinor helicity things, you have to take momentums to be complex. Does your comment also hold for that also?
I mean, that would in the end be some... it would hold for the final amplitude, right? In the end, you do whatever you do, but you get a final amplitude as a function of the polarization and the momentum. And then there will be a constraint on that final amplitude which comes from CPT.
Right.
Now, I was wondering whether that, you know, like I was saying, it feels like from just group theory point of view, spin 1 and spin 1 -1 have nothing to do with each other.
Yeah.
But we know that that's not true, right? We know it's the same field, namely the gauge field or the graviton, that creates both spin 1 and spin -1. The interactions of the spin 1 are related to that of the spin -1.
I see. Okay. I don't have a comment right now on that series right now, but let me give one example and then maybe we can talk later about this series. So, you know, let's take TOO. Let me just do a epsilon transformation. I get this result. If I take E goes to 0 limit, I get this result, okay? And then E goes to 0 limit, I'll definitely get K1.Z3 square. This correctly reproduces the spin S OO covariant amplitude. This thing, you know, you cannot write it. This thing you cannot write it as a covariant. This thing you can show because in 4 dimension there is no covariant thing that can appear, right? So you cannot really write down this as a covariant thing in 4 dimension, but you can actually convert them into spinor helicity variables, and then they actually correspond to this structure. Now what Siraj is saying, maybe from the 4-dimensional perspective, I don't know, Siraj, whether that will relate. For example, your CPT will relate this to this. Is that what it is going to do?
Yeah, if one of them is positive polarization and the second one is negative polarization, meaning if one of them is spin 1 and the second one is spin -1, then certainly it would.
Yeah. So, for example, if it is spinor helicity is minus. If it is helicity plus, you can show that for flat space amplitude, only one of them can exist, either minus or plus, by something. So actually, said I do not know to precisely your answer, but the comment I want to make is that if this is what is the CPT does, then maybe it is not then the CPT transformation. It would be something else. So I don't know the answer to that question.
Yeah, it just seems to me that if you have an amplitude that is CPT invariant and obeys all the group theory, the spinor helicity tells you that it obeys all the group theory, right?
Yes.
And then what's left is CPT. If you have both of those, I think you will get a Lagrangian. Or unless I'm missing something very.
Okay, I do not know about that, but I think that no one. I think all the spinor helicity things, people just stop at it, and CPT thing, I don't think people discuss much. Like, how can I get a Lagrangian to get all this extra thing? There are very less, discussion about the.
Yeah, just one last comment, which is sorry, but one last comment is that any higher dimension, in 5 or higher, this issue would not arise, because then all polarizations are part of one non-abelian. The little group becomes non-abelian.
Yeah.
Becomes SO3 or higher, and then everything is by group theory part of the same amplitude. It's only in 4 dimensions that you need that extra CPT condition to link the 2 different polarizations.
I see. And exactly as you pointed out, sir, in higher dimension, this problem does not arise.
I see. Okay, fine. Yeah.
There are some recent works where people actually define something called chiral higher spin gravity, where they exactly take this extra amplitudes and then just write down a Lagrangian which is based out of this extra amplitude, and then they show that these are not local or anything. They don't demand any covariance or anything. They just write down in a particular light cone gauge or something. And they show that they are actually consistent theory in the sense that they have nice UV property, 4-point function, etc. Things work out well. So there has been some actually study about the same chiral higher spin gravity, but about the CPT, and they don't insist on writing a covariant Lagrangian. So, CPT, I have not seen a consistent discussion about that.
Okay, thanks. It may be wrong what I'm saying, but okay. Yeah.
No, but we can actually look at it. Yeah. Just to summarize here, we have seen, this part of it has a very nice interpretation in terms of, if I take the flat space limit, it exactly reproduces the flat space scattering amplitude. What about these extra structures? Do they play any good role? Actually, it turns out, yes. And that is what Sandeep was actually mentioning. This was a very nice paper by Sandeep, Ashish, and Vishal. They computed in alpha vacuum the 3-point function of operator. And it turns out that they got all the structures, and precisely if you consider this alpha vacua are just, if you take the bunch divisor, which is the usual vacua that we are used to, it's a squeeze state with this kind of definition of alpha vacua. Then if you calculate the correlators in this, you precisely actually you start not only these things become important, but also these things also start playing a role. Okay. In the results, some particular combination of this and this comes. It comes out very nicely consistently. With Sandeep, Suman, Sunil, my student, so we are trying to understand various things. Some although these are a nice aspect, but some phenomenological aspect needs to be understood very well. So right now we're just trying to explore this thing. But an interesting, curious observation is that those extra things, Abhijit, that you were asking, do they correspond to anything? Actually, they appear in cosmology very nicely. Okay. Okay, so now I would actually finish very soon. So one thing that we see that there is a connection to flat space S matrix. is the connection just, do I learn anything new from there? Meaning, I'm just taking a CFT equator, I'm taking a flat space limit, and I'm getting a flat space amplitude. What do I learn about it more? So as a test of it, we did the following calculation. This was suggested earlier in the literature, but not really understood very well. We did the following calculation that, in the flat space amplitude, they satisfy some kind of a double copy relation, which is if I take 3 gravitational amplitude, I square it, I get, 3 photon amplitude, if I square it, I get 3 gravitational amplitude. We did precisely the same calculation in the CFT 3-point function, and actually what we could show that the double copy relation actually works very, very beautifully. The way it works is also very interesting. The 3-point function, if you write down in terms of non-homogeneous and homogeneous, the double copy is roughly, you take non-homogeneous square separately and homogeneous even and odd separately, and then square them, and then the double copy works. Okay. So roughly what happens, if you take spin S1, S2, S3, and spin S1 prime, S2 prime, S3 prime, if you square them, you get even S plus S1 prime, S2 plus S2 prime, S3 plus S3 prime homogeneous answer. Odd times odd actually also gives you very nicely just the even answer. Spinalicity makes it totally clear, but odd times even gives you the odd answer. Okay, so that is the structure that appears. You have checked it explicitly. It works out very nicely. For example, if you take JJJ 3-point function, you square it, you precisely get TTT. Okay, and if you look at the answer before we actually understood spinalicity, the momentum space answers are very, very complicated. We had to work really hard to actually get this result. Then only later on spinalicity they become much like trivial. But the point is that even though the answers are very complicated, the double copy relation works. And this result was not understood in position space. So somehow it indicates that the analogy with the S matrix actually is a very fruitful something and fruitful direction. And we believe more general results of S matrix finds direct generalization in CFT. For example, unitarity, causality, those things. For that, I have to go to the Lorentzian version. BCFW scattering equation. There are some work in the de Sitter or anti-de Sitter or the BCFW, but it's not as if like a CFT statement from the kind of way Subrat had a very nice work and the follow work for some particular diagrams that there is a double BCFW recursion relation kind of thing. But I think these are the things will in general hold. Okay, so we are actually investigating some of such results. That we are just investigating some of these things in the CFT language, how they hold, how much of them hold. Okay. So whatever I said has a very close parallel to in de Sitter and in anti-de Sitter. It turned out actually in de Sitter, anti-de Sitter, people did some kind of spinalicity formulation in anti-de Sitter. And there were also very similar confusion, and they were not very sure how does it match with the CFT equator. Those things got very nicely. We understood them a little better than what was understood by making the connection. So what I want to point out, there's a very nice connection also with the calculation, similar calculation in anti-de Sitter, etc. Okay, so I'll very quickly just finish this thing with some results, 3-point function and the 4-point function results that we obtained in Chern-Simons matter theories that I'm going to very briefly mention, unless there is some questions. No. Okay. Sorry, am I audible? Am I still there, or
yeah, yes, Sachin.
All good. Sachin's totally stunned. There are no questions.
People are really bored. Or
I have a question. When you say that these correlators are related to scattering amplitudes, what exactly does it mean? Because correlators are just say propagators that are joined to each other at the ends. Now, in order to go from there to a scattering amplitude, you would have to have correlators that you would have to have propagators that propagate and then scatter of each other, which are totally different things. So, in what sense are you saying that?
Yeah.
They are
so, in what sense I said this is the thing I was trying to show you earlier. That given a CFT equator, if I take if I define a particular limit, while defining that particular limit, you roughly think about things become like a scattering amplitude. It's in the taking that limit, and then you are able to read off the residue of some particular poles as the scattering amplitude. Okay, in that sense. So I'm not thinking from in particular some Feynman diagram perspective or etc. Just abstractly given a mathematical expression, if I take this and I'm able to reproduce the scattering amplitude. If you are asking how does in momentum space suddenly become something as a on cell condition, that comes out, but you have to complexify the momenta, etc., and then you would be able to show the asymmetric structure comes out. Those are little details, but yeah.
Okay.
And this connection between correlators and asymmetries, is this restricted to 3-point functions, or is there some claim?
Yeah, so connection between asymmetrics and this thing was actually pointed out along in Penedon's work in the Milling amplitude. Milling amplitude 3-point functions are trivial. For 3-point function, people pointed out for 4-point function, some result exists. It's not a very consistent set of results that exist. Some result for 4-point function, some particular exchanges it exists, etc., etc. It's not a very well understood, but it is believed to exist.
This and the connection goes through Mellon space, you say?
No. Connection, as I said, like right now it's just an observation, Siraj, that I calculate in momentum space, I take this flat space limit, I take the particular residue, it precisely matches with the results. Okay.
I see. So for instance, to get a pole in flat space,
yeah,
that will come out of some particular cross ratio kind of function in correlator. Space. So what would be the connection? So now there are an infinite number of amplitudes on both sides.
Yes. Yeah.
And but you say that all the constraints satisfied by one structure are also satisfied by the other. That's the same set.
So right now what is established is a particular exchange thing that people understand. As a full thing, I think in momentum space, as I pointed out, this thing is not known in momentum space. What is the general structure of momentum space spinning correlator? That is not even known as of yet. The scalar thing is known. That's very complicated. I think that general understanding is not there. But exchange by exchange, people have some calculation done, and general thing is not understood.
Sorry to slow you down, but exchange, I understand what you mean by exchange in the bulk. But what are you comparing that with in the boundary?
Yeah. Right. So if I'm, it's like in a CFT calculation. If I have some primary operators that is getting exchanged to calculate for me, it's like 3-point times 3-point some propagator. That kind of structure in CFT, for example.
Block.
Yeah. In momentum space, it turns out that the blocks are very easy, right? It's some because descendants are some derivatives to and they become just p mu some structure.
But block by itself is not crossing invariant. Do you mean like Rajesh's blocks? These are ADS blocks?
Yeah. Sorry.
Why do you want it to be crossing invariant?
Because if you're computing a 4-point function of 4 equal operators.
No, I mean, maybe he's matching it with only a channel exchange.
I see. Is that the case, Sachin?
Yeah, that I think you can do, Siraj, that you can. I have not actually done any of this 4-point thing.
Just one comment. I mean, Penedon is sorry.
Yeah, go ahead.
No, just one comment I had was that Penedonus and collaborators recently wrote a paper called Scattering Amplitude for Conformed Field Theory, where they essentially worked with CFT correlation functions in momentum space and defined a sort of LSZ prescription. And they were able to identify the resulting object as some sort of scattering amplitude, but what exactly it is the scattering amplitude of was not very clear. In particular, they were not, I think, able to assign any bulk interpretation for it or any, So this 3-point function matching with 4-point the scattering amplitude, I wonder whether it's some kinematical story or actually some bulk, if there is any bulk relation to this. I'm not sure whether there's some flat space limit actually going on, or that's what I was kind of not very clear about why that E going to 0. That seems like a some weird prescription to get. Why is there the flat space limits, etc.? These questions are not clear to me.
I see. I thought you were going to explain to me that this is what happens in ADS if you focus things in a small elevator region. Okay, there's no explanation like this for the E going to zero limit. Okay, now explain later to me if.
I mean, yeah, okay. I also don't know. I mean, usually I think of some large energies, right? You need to have large energies. So this is weird limit. Maybe Shiraz knows better.
No, but also 3-point functions, none of, at least the story that I understand has a story for 3-point functions, right? I mean, it's all associated with developing singularities in cross ratio space.
Yeah.
3-point functions just determined by symmetry.
Yeah, that's why I was wondering whether it's just a kinematical thing. It's not really a bulk thing. I was wondering. Because in Penedones's case, he actually does this for 4-point functions. Yeah, and he gets some interpretation, but it does not go towards interpretation of any scattering process in the bulk. He has some section saying, okay, there's some scattering amplitude we got, and what exactly is it scattering amplitude of? Then I think he just wants to interpret it as a CFT object itself somehow, some probes scattering off of CFT or something like that. But that is not clear to me. And he probably doesn't have that E equal to zero limit.
For me, I think what is more important is rather than to make a connection, there are some result in S matrix. What is more interesting for me is that I think similar result is an intrinsic CFT structure, similar result without making a connection to the flat space amplitude. Those similar intrinsic result should also exist in the CFT in some so for example, just to give a from the de-Sitter perspective, if you calculate 4-point function with a particular exchange, okay, JJOO with some maybe a particular exchange or TTOO with the exchange of, let's say, graviton, graviton GGO scalar with a graviton exchange, and then you take you observe that actually there are various pole structure that appears there. Okay, for example, there is a 1/E pole. Then you will also find out there is a 1/EL pole. You will find out 1/ER pole. What you find that 1/E, so EL, ER are basically EL will be something related to this left half part of it, like maybe K1 vector. There is some EL and ER that I had to remember now. But what happens is that the 1/E pole, this residue precisely matches with this amplitude in 4 dimensions. Okay. That is the kind of connection that is very that is explored. But a more general kind of thing, as Shiraz is asking, like, is it understood more like structurally, S matrix structure? That I don't think in momentum space is understood. But what I feel is interesting is that rather than asking what exactly their interpretation, this some result in S matrix I think would find natural generalization in the momentum space CFT equator. This is based on some simple observation, but I about that we need to explore more. Okay.
Doesn't this have? Sorry, go ahead.
Just one thing, and then please go ahead. Already there's been a lot of discussion, but even for 3-point function, I wanted to ask Shiraz and Abhijit and you, Sachin, shouldn't there be, at least with suitably analytically continuing the mod case, some way to relate it to a scattering at high energies, in some small region of ADS, kinematically, and thereby related to flat space scattering, and then use the same kind of thing for higher point correlators? Is it senseless to try and think of a general relation like that between flat space S matrices and at least bulk ADS?
Shiraz will just correct me. For them, at the level of 4-point function, they try to understand something where it was very important for them to understand there are some singularity structure. Those they called as bulk point singularity. But in 3-point function, it was not very clear what is as there is no such analog, right?
Okay. Anyways.
Yeah, I think I agree with Sachin. I mean, maybe there are some ways, Sandeep, that I haven't thought of, but
can't you make the 3 things collide in very high energies? What does it matter? We might be in ADS space as far as CERN is
Yeah,
concerned?
it's sort of difficult to get three massless particles to collide on shell, right? I mean, unless it's purely forward,
Okay.
right? Just kinematics forbids that, right?
I see. And a mass in flat space will become something very massive.
And if you, in the limit that at least we worked in, the masses are all small compared to the energies, so it didn't matter. So to get real scattering, in some sense, we needed a fourth point. You know, for the usual reason that 3-point things are difficult in real space to put on shell. Yeah. But of course, you can get around this by going to complex something. And maybe so there's some way that I haven't thought of.
Okay.
Also, this intuition, right, as Sandeep said.
Yeah, go ahead.
No, as Sandeep said, you had this intuition of sending it with very high energy, right? I mean, even Shiraz's process, things happen at very high energy. So why would a low energy, a zero, E equal to 0 pole be relevant?
Yeah, no, that, yeah. I thought after some continuation, E equal to 0 is like energy conservation, but each individual energy is high. Okay.
But it's he took it, I think, in the discussion, there was some relevant point where you only want to look at the term which was K1 plus K2 plus K3. Yeah, so it's a bit confusing to me.
Okay, I'll bug you all.
And just one more comment about this de Sitter calculation that Sachin was talking about. Yeah, there indeed they have some way of computing these diagrams, but there, you know, a lot of things are different. I mean, they are not quite Fourier transforming the CFT correlation functions, right? They are just doing a particular diagrammatic calculation in de Sitter itself, right? Yeah. Let's say Paher or Baumann and collaborators and so on. They're doing a particular calculation with Green's function, which are a bit weird, associated to Dirichlet boundary conditions, etc. And then they are finding this relation. So it's not quite, you know, starting with some CFT correlation function and taking this Fourier transform and then taking a limit. I feel.
I see. Okay, thank you.
Yeah. Sachin, just to say, I'm going to have to go and pick my daughter up from school in about 3-4 minutes. So
yeah, so I'll actually just give. I'm sorry for going very long.
No, I'm sorry for.
No problem. So let me just give you a summary of if I just apply all this result to higher spin theory, what it turns out is that you get a very nice picture, which is that you start with a free bosonic answer correlator. You deform that answer with appropriately with a phase. This is what we call anionic phase, and this phase appeared in 2-to-2 scattering. And if you change the coupling constant, you reach to free fermion theory. And in between, you actually get the interacting higher spin theory. With the same analysis, you also predict that the supersymmetric theory can have only 2 maximum structure. And that was actually conjectured some time back, but without any extra calculation, you can actually do that. And this summarizes whole answers for slightly broken higher spin theory and higher spin theories. You can do it for general theories. For general theories, you can actually, it turns out this writing results in spinality variable has a very nice interpretation in terms of conformal collider bound, and conformal collider bounds actually just bounds the homogeneous coefficients as it is expected, because the non-homogeneous coefficients are determined by the 2-point function. Homogeneous coefficients are the 3-point function, OP, those things. It turns out the picture is the following: that higher spin theory lives on the unit circle. Any CFT will always live inside. Holographic CFT even will live inside of a that is what all the conformal collider bond that was done in the calculation actually becomes a simple. So I just quickly want to just comment on the 4-point function. This I think is something that we are working. We are trying to ascertain few things. Let me just show you one non-trivial example, and then I'll just conclude. One non-trivial example: suppose I take a spin JJOO, this 4-point function for Chern-Simons matter theory. This can be written as some exchange of spin S. I'm talking about only primary operator. There are double trace operators, and then JJJS has 3 structures: free fermion, critical boson, and parity odd. Now I'm going to use this fact that the parity odd can be written as epsilon transformed of free fermion and the free boson answer. Using that thing, you can show that the 4-point function of JJOO naively have the structure that is JJOO free fermion, JJOO critical boson, and JJOO free fermion minus JJO critical boson with a epsilon transformation at the level of 4-point function. It turns out that if you actually try to do Feynman diagram calculation is a bit difficult, but if you try to do a higher spin analysis precisely solves this. With this answer, if you just plug that back into higher spin equations, the higher spin equation is something very complicated, but with this simple analysis, you see that the answer that you get by doing that naive analysis gives you precisely the higher spin, solves the higher spin equation. It's a little stronger condition that I'm putting on the higher spin equation, but at least I get a consistent solution. And then let me not take too much time. And if I actually calculate TT 4-point function, in general, these are very complicated calculations, as you know, in general CFT in Chern-Simons theory. It has 5 structures, x0, x1, x2, x3, x4, out of which 3 structures are parity even, 2 structures are parity odd. And this is a simple analysis. Simple analysis that I explained gives you this, that x4, x2, x0 are written only in terms of free theory. This x3 and x1, these are parity odd thing. You also get some result by solving higher spin equations, but that is very, very complicated right now. We have not yet fully understood.
Sorry, Sachin, just so you're doing this now in this is in Chern-Simons matter theories or in general?
Yes. No, I'm doing Chern-Simons matter theory. I'm applying all the previous observation to Chern-Simons matter theory. Got it. So, 4-point function, very less result exists, but, with this analysis, we get some results, and which actually turns out to be consistent with various other analysis. We have to do much more to be able to confirm, but these are the naive expectations, okay? Now, I just want to finish by this part of this discussion is that, it looks like at the level of 3-point function, I was able to generate all possible 3-point structure just starting from a free theory. At the level of 4-point function also, the answers, if you look at, they are just given by free theory answers with some epsilon transformations. And CFT, TTTT, I have not yet understood this thing in terms of that, but I believe there will be some such simple interpretation in terms of free theory. So it naturally gives rise to the question. So inverse phase structure for Chern-Simons matter theory in the low energy limit, which is what is opposite to what Shiraz was considering in his paper, does it correspond to a free theory with some identification, some constraint? Because the result 3-point function, 4-point function result indicate that. So we are trying to understand that point a little better. So basically, one way to understand that question is that if I write down higher spin equation, slightly broken higher spin equation, I have showed you how to generate the breaking term in terms of free theory. So somehow higher spin broken equation for slightly broken theory, I should be able to rewrite for exactly conserved higher spin equation. If I am able to do that, then I have proven at least that all the 4-point, 5-point, whatever point function would exactly behave like that of a free theory. Okay, so that is one analysis that we are trying to understand. Yeah, so I'll just end.
Sorry, Sachin, very quickly, not to slow you down, but high and low energy means energy scaling with N or some combination of N and Toft coupling. Or what?
Yeah. So by high and low, what I mean, Sandeep, is that whether you take scattering states or whether you take bound states, like for operators, J is like 5 or 5. It's like a bound state up to scalar. That kind of analogy I'm talking about. That where bound states are more important.
I see. Okay, got it. Okay.
So what Shiraz Shiraz and other people did in the paper was the other limit, if I understood correctly. And what I'm talking about is this limit.
Okay. Thank you.
So I'll just conclude with this slide that you can read. I find the connection with the asymmetric CFT structure in momentum source is really interesting. 4-point function people have really not explored much, and connection with the asymmetrics is really interesting. That I think will give rise to various interesting developments. And there is a very nice connection with the if I take the soft limit of 3D CFT answers. Because 3D CFT answers are related to 4D amplitude, if I can define some intrinsic soft limit of CFT, I should be able to see, some connection to the celestial holographic kind of stuff. That would be interesting to see. Lorentzian version would be really interesting, and connection with the de Sitter or anti-de Sitter, those kind of things will be interesting to explore. Okay, sorry for going really over time.
Let's thank Sachin for a very nice talk. If there are some questions, please go ahead and ask.
I just want to ask a question for later, just for discussion again. Sachin, the sort of soft limits in de Sitter, which are called squeezed limits, like Maldaceno's limit, they seem to have some connection vaguely to me with the kind of limits considered, soft limits considered for celestial holography, etc. Is that something you've thought about? Is there such a connection? What do you think?
No, I have not thought about. I spent a little time, Sandeep, and I have not really thought about that thing. But it sounds very. There are various things which sounds very similar. De Sitter, again, the symmetric group is SO4,1 something. It has all this complex representation. If you look at celestial holography, that also has all this complex representation. There are various things which are very recently, there are various norms that you can define which are very analog to in de Sitter norms, etc. The stories are very analogous. I have not explored, but yeah, there seems to be some connection.
Okay, thank you. Thanks a lot.
I have a question.
Yeah.
Like in the normal ADS CFT correspondence, when you have these, say, suppose you take Rajesh's second paper on ADS CFT, those are early 3 papers. In that, he derives the bulk to boundary correspondence by doing the following thing. He takes a certain, say, a 3-point function, a 3-point correlator, and then he kind of converts the delta to a tree in the same space, and then he promotes that to ADS space. But before promoting to ADS space, he has the tree in the original space. Suppose you start off with 3 dimensions, you would have a tree which is like a decay process or a scattering amplitude between 3 particles in 3D space itself. So I'm just wondering whether this connection between scattering amplitudes and correlators in the same space can be thought of as being the sort of analogous thing that Rajesh did. I mean, before promoting all that to the ADS space, you have the kind of the 3-point scattering in the same space itself. I was just wondering whether there's a connection with what you said.
Maybe I have not really looked into those papers, but but yeah, okay, there may be some connection.
Okay.
If there are no further questions, let's thank Sachin again.